Ladies and gentlemen, please welcome Mr. Navin.
Hey guys, thanks so much for having me here. First of all, thanks for that introduction. It's very relevant to what I'll be talking about today. First of all, thanks to the organizers for like a great set of sessions that I've gotten over the last couple of days. I've really enjoyed myself. So thanks to the organizers. So coming specifically to my talk, right? So what we're going to be talking today is primarily a little bit about deepfakes, but I think what we'll also be talking about is how neural networks work with images in terms of image generation, in terms of image manipulation, in terms of all those things that like kind of blow your mind at first sight. But then we'll break down a little bit deeper within the systems to like understand how these algorithms work, how these networks work, what are the different applications of these networks, and so on and so forth. Okay, so the title is obviously that I've chosen for this talk is called Rubs Eyes Vigorously, because usually when you see any of these results, right, the first reaction that you'll have invariably is to not believe what you're seeing. And then obviously all of us go through this journey of like starting off from there, and then we like break it down as engineers, we like try to break it down as practitioners, and we'll go ahead from there. So before we start off, a very quick introduction about myself. I'm Navin. I go online as Mad Max. I work at this company called Tact. I'm originally from Goa, where I also did my bachelor's degree from. Then I did my master's at IIIT Bangalore, where I specialized in AI and machine learning. I've been involved in tech more or less for the last 13, 15 odd years, and working with AI for the last 8 to 10 years, I guess, in different forms. I'm working with deep learning primarily for the last 5 to 6-ish years. And usually I tend to work full stack. I've gotten the great opportunity to work on a lot of different specific areas, not purely in terms of research, sometimes in research, sometimes in applications, sometimes in high performance engineering, sometimes like even on the front end side of things. So that's been kind of my comfort zone, is like dabbling around with things. So in this talk as well, we'll kind of dabble around quite a few things. So primarily what we're going to talk about is in this talk about deepfakes. I will talk about CGI, we'll talk about neural nets, obviously, we'll talk a little bit about loss functions, autoencoders, we'll talk about PyTorch. A lot of deepfakes actually involves one specific clever trick, and we'll talk a little bit in detail about that trick. Um, Anything that you do about deepfakes, you cannot really get away from the ethicalities. So we'll talk a little bit about the ethicalities as well. And we'll talk about GANs and other forms of image generation. And we'll try to keep it as, we'll try to include bits and pieces of code wherever possible. If not, on my GitHub, there are a bunch of links, a bunch of notebooks that you can try out, you can play around with to actually get a bunch of these results almost as good as them. Specifically with respect to math, we're going to keep this talk very light on math. It's very easy to like get very involved within the math of why things work a certain way. We can talk about that offline, but since we have only 30 minutes, we're going to keep this incredibly light on math. And obviously the disclaimer that comes at the start of this talk is a lot of this work is very derivative. Most of this work is almost entirely done by other researchers. I'm merely a practitioner who's been trying to figure out these methods and trying to see whether we can make improvements upon these methods. A lab that I'm part of actually works on these methods as well, and they are publishing papers as well, but none of this is like purely my research. So to get started, right, when you say deepfakes, I think for a lot of people, deepfakes came into public perception through one of two videos, right? One was a set of videos that came up on Reddit back in 2017, and we'll talk about those a little bit later. And those who know about what I'm talking about, let's just leave it there. But for a lot of people, the time that deepfakes came to popularity was when BuzzFeed actually released this video, and I'm just going to play it for you guys.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is Going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you. Stay woke, bitches.
Awesome. So as you can see, that video had Obama saying a lot of things that he would not normally say, and that just kind of where deepfakes kind of shot to fame. And obviously, with the reach that BuzzFeed had, kind of was covered by a lot of other news outlets as well. And then people started buzzing about what exactly this is. Oh, this is so mind blowing. How does this work? Can I not trust anything anymore? And so on, right? So then obviously comes the next bit of it, which is as engineers, we start looking at it from how this might have been implemented or how we can get something like this done, right? So let's start off at the base, right? When we talk about deep learning, what are we actually taking? When we talk about a neural network, at its simplest, this is what we're talking about, right? We're saying we have an input layer, you have an output layer, and you have a bunch of hidden layers in between. If you're someone who has a lot of money, your hidden layers is going to be a huge number of hidden layers with a lot of states in between. If you're doing something trivial like say MNIST, you're going to have like fewer layers. You don't really need too much complexity. Then these layers are what you're in the deep learning world, you say they capture your features, so to speak, right? So these features are nothing but at the lowest layers, you're talking about gradients, you're talking about lines, you're talking about shapes. Then at the deeper layers, it's like more involved features, like maybe if you're identifying a human face, then you'd have an eye and a nose and a mouth and so on and so forth. And this hugely important development, which is like the propagation. So anytime any error comes in, you actually, if you detect an error going forward, then you actually propagate it back as well, and then you keep improving over time, right? An important thing to realize is that most of the things that we're talking about in terms of neural nets, right, are not really new research, so to speak, right? We've been talking about them quite a bit in the last 4, 5, maybe 10ish years, but all of these are the foundations for these are laid long back, right? In fact, like if you talk about AI specifically, I think Alan Turing has spoken about how machines can be intelligent using a neural form of intelligence back in the 30s or 40s. So, and these are like papers that I have published back in the 40s and the 90s and the late 80s, sorry, which are actually setting the foundation for what we're talking about today. It's just that we have kind of gotten to a state where in terms of GPU processes, in terms of the way that we write code, in terms of pure hardware capability, that we're able to generate a lot of these things and bring them to fruition, right? Now, one of these things which is very cool about the way that neural networks are that neural networks under certain constraints are universal approximation machines, right? So basically what they say is that you can approximate any function in the world. Now that sounds very weird because as a mathematician, when you say approximate anything, it has a different context altogether. But as engineers, what we're trying to say is that you can generate great outputs given great inputs for any problem statement, as long as your problem statement is defined, as long as you constrain it in some way, as long as the data is good, as long as you have enough computational power to like generate the model and so on and so forth, right? For a lot of use cases, the compute power required today is still very large. The data set still does not exist. The data cleaning methods are not there, augmentation is not there, and like over the last 4 days, I think a bunch of people have spoken in detail about all the cons with talking about neural networks as do anything machines. But by and large, what it means is that we know, and it's been mathematically proven as well, that neural nets can approximate any function up to a certain degree of approximation. So now let's go to the next part of it, right? Now that we know that we have this lovely concept called a neural net, and we know that it can approximate anything. So how about we get it to approximate a very specific problem, right? So let's go on to a neural net that we have trained, let's say with a certain data set to generate images of human beings, right? So what if I told you that one image in this is generated by a neural net, and the other image is actually is an actual photograph of a human being? Now, in your mind, I would want each of you all to like just go and figure out which one do you think is generated by the neural net and which is which is an actual human being, right? Left or right? We can look at left as A and the right as B. So have it in your mind, whichever your answer is. So we'll go on to another example here. You have the left is A and the right is B. Again, one of these, let's say, is by a neural net, and the other is an actual human being's photograph. And if you have your answers, we'll go to the next one. So this is a slightly harder one because they're not directly comparable. The left is A and the right is B. Now I'm assuming that there'll be some part of people who would have said that the A's are always generated by the neural nets and the B's are actual photographs. There'll be some people who would have said that the B's are neural net generated and the A's are actual photographs. But the fact is that almost everyone is wrong, right? Because if you notice the star at the top, right? The star is because actually all of these are generated by a neural net. So all of these examples are actually from this website, generated by the website called This Person Does Not Exist. And you can go and click on it right now and play around with it. So every time you hit refresh, it's like generating a new face for you. And the way that that system has been trained is using this neural network architecture called a GAN. So a GAN basically is a generative adversarial network, and we'll talk a little bit more about it in the next slide. And that's the training is for a GAN is the most important bit, right? Because for a GAN, the problem is you never know how good your convergence is. Now, specifically what This Person Does Not Exist, it's actually work that's derived from a specific research paper that was written. And the way that they did it was they gave it 1 million plus images of men, women, and children, and then like train the system to like identify what a person is, so that it can so when you tell it to draw a human being, it can draw a very photorealistic human being. Now this is really great, right? So basically what you're saying is we have neural nets that are able to generate these photorealistic pictures of human beings. But the catch that you have is an understanding that at the core, the network itself is very naive, right? A lot of it depends on your architecture, depends on the data, depends on a lot of these other features that may or may not be particularly in your control. And an example of that is shown below, right? For us as a human being, it's very easy to see that this person is just a man wearing an eye patch with a red cap on his head, right? For a neural net, it's not that simple, especially if a neural net has been trained on a data set which is only made up of people, and all the people have 2 eyes, 1 nose, 1 mouth. Then what the neural net thinks is that a person has to have 2 eyes, otherwise it's not a person. Now, whether you think of it as a feature or a bug, that is up to your interpretation. I think in one of the earlier talks, Ben actually spoke a little bit about this as well, where he had his eye and his ear interchanged, right? And for a person, you know immediately that, okay, I know what this is, but something's fishy because the eye and the ear are interchanged. But for a neural net, that understanding is very, very hard to get. So once we have this understanding that a GAN is actually a pretty naive network, let's see like how we can use that to our benefit. So to explain what a GAN does, right? GANs were actually introduced by this researcher called Ian Goodfellow. And an easy way of introducing it to someone who layman is basically to say, think of Among Us as the game, right? And Among Us, it's basically the same concept except codified. You have two parts of the system. One's called a generator, one is called an adversarial network. The generator's job is to generate images which are as close as possible to real images. The discriminator's part is to actually figure out which is a real and which is a fake image. So as you start training, the generator keeps generating better artificial images, and the discriminator actually gets better at identifying which is counterfeit and which is real. And over time, because this training and what we spoke about before, right, where your loss function actually determines that your every error is actually propagated back to both the discriminator and to the generator becomes extremely good at creating a counterfeit network, creating a counterfeit image, which is exactly what we want to do in the game Among Us as well, right? You want the imposter to have his behavior as close as possible to a crewmate, but at the same time, what the imposter is doing is totally different to what a crewmate has to do, right? They are actually adversaries to each other. But the best imposters are those who are like as close to a crewmate as possible. And that's kind of the core philosophy of what a GAN does. So now that we know that we can use these networks like GANs to like generate images, the next bit that we talk about is how about swapping images, right? If you want to do a face swap, then there are traditionally a very, very standard method that's followed. And that's shown here. For any one of us who've seen the Avengers movies, you're probably familiar with the guy on the bottom. That's Bruce Banner, or the Hulk as we know him. And actually the way that a lot of movie studios work on this, and I was very lucky to see this firsthand when I worked at DreamWorks, is that they actually have these models that are created which have a bunch of these movable muscles, right? Which are created in Maya or like Blender or like a bunch of these other software that they have. And what they do is they actually have these motion capture rigs, and like facial motion capture is usually done using these dots. And then what you're trying to do is, as a process, is just this, right? You create a model with markers for every movable muscle. Then for a face in the frame, you have to identify the location of each marker, and that's what the dots are for on the face of Mark Ruffalo there. And then in a model for each frame, what you need to do is move the corresponding marker to the right location. So a smile would mean like move each marker to make a smile, and then go to the next frame, again do it. right? And that model actually is something that has been traditionally used by film studios for as long as you can imagine, right? You've probably seen things like Star Wars, where the characters who are dead were brought back to life. It's been done in a bunch of places. A lot of animation movies use this motion capture as well. I think Shrek used it quite a bit as well. So that's kind of standard way of doing it. But now let's look at it from a engineer's point of view, right? How can we actually use neural nets to do the same thing? So the first thing that we spoke about in this was from a frame, you want to identify the face. Now, thankfully for us, like facial recognition is something that has been studied for a long time, right? Like OpenCV itself offers a bunch of libraries to actually do it, but like my personal favorite when I do any sort of facial recognition task is using MTCNN. So that's a multitask cascaded convolutional network. So that itself is actually behind the scenes another convolutional neural net that does facial detection. And it is amazing in terms of accuracy. As you can see in the picture, this is actually the output for that was actually described in the paper itself that they published. Those are the famous Oscars photos with everyone. And you can see that literally everyone's face has been identified. And the nice part is it actually has markers for you as well. So and we'll talk about why these markers are important, because the markers tell you where the eyes are, where the start of the mouth and the end of the mouth is, and where the nose lies. Right? And these markers are very helpful for us going forward. It's literally 4 lines of code to use this. You just do a pip install and then you can like actually run this on any image that you have. Ridiculously easy to set up, but amazingly accurate. So now we go to the next step, right? Now that we have identified a face, now let's take the same example that we had before. Let's say we have an image and we have identified a face in it and we want to swap that face with someone else. So this is where the fun bit comes in, right? Which is where we use this neural net called an autoencoder. Now an autoencoder is a different neural network to a GAN, but I think the understanding for GANs and autoencoders are kind of self-explanatory, right? A GAN kind of tries to create new images using data that it's heard in the past, that it's seen in the past, whereas an autoencoder is again 2 parts. One is called an encoder and one is called a decoder. So the encoder's job is simply to take an input and generate a very compressed encoding of it. Now that encoding can be a bitwise encoding, it can be a set of tensor variables, it can be anything that you want depending on the use case that you're trying to examine. But what an encoder basically does is it tries to capture as much information as required for the original input, so that the decoder, which actually looks at the compressed input and tries to reconstruct the output. The way that the network trains is fairly obvious, I'm guessing at this point, which is that you take an input, you generate the representation of it, the decoder tries to reconstruct, then we do a diff between the original input and the reconstructed input. And then we like try to say what the loss is, the loss gets propagated again to both the encoder and the decoder and so on. So for the GAN, we use the example of Among Us, right? For autoencoders, a simple example that I'd give you to think about is think of it like an exam, right? So you have a textbook and a textbook has like 10 pages worth of data in it. So when you make your notes from the textbook, you have like half a page of notes at best maybe. And then when you come to a point where you go to the exam and there's a 10-mark question asked and you need to pretty much write out exactly what is in the textbook, you try to go back to your notes and try to write down what is in the textbook using those 4 lines that you've written in your notes. A lot of times it's not going to be great, obviously, which is why all of us, at least for the backbenchers, it's got to be very relatable that your notes do not really reflect anything that's in the textbook. But over time, what's going to happen is if you get better at getting notes, then actually what's going to happen is your 10-mark question answers are also going to be better. And that's going to be more similar to what's going on in the textbook as well. So that is kind of like the philosophy behind how autoencoders work, right? So far it might seem like we've spoken a lot about a lot of tech, but we've still not spoken about face swapping at all in any way, right? And this is where this one cool trick comes in, right? So we'll talk about training. So training for any sort of face swap model, by default, the way that you do it is you have one encoder, but you have 2 decoders, right? So the way that it works is when you're training, what you're going to do is you're going to give it an image of Jimmy Fallon for the encoder. Usually the way for training to keep it different, you like actually add a source of noise as well. You'll warp the image in some way, you'll flip the image, you'll do something. And then the decoder for Fallon, which is decoder A in this case, is responsible for creating a proper image of Jimmy Fallon. The same encoder is also at the same time learning to create an encoding for Jamie Oliver. And at the same time, the decoder B knows how to decode Jamie Oliver. So now if you look at it, the encoder is able to encode for two people. One is Jimmy Fallon and one is John Oliver. Sorry, I got the name wrong. John Oliver and Jimmy Fallon. But the decoders are actually specific only to the person, right? So a photo of John Oliver, which has been warped, given to decoder B, will actually give you a proper image of John Oliver. Whereas if Jimmy Fallon, encode it, give it to decoder, it's going to create an image of Jimmy Fallon. We keep doing this as part of the training until you Hey, can you still see my screen?
Yes, we can still see your screen. You were freeze out for a second. We can still see your screen.
Yeah. My internet conked off for a second. I'm sorry about that.
Okay.
Yeah. So this is where we come down to a really clever trick, right? So what we actually do is, if you noticed, our encoders now been trained to like generate encodings of both John Oliver and Jimmy Fallon, but our decoders are trained on the specific person, right? So this is one really clever trick that we do, which is that you take an encoding of a photo of Jimmy Fallon, you encode it using the same encoder that's been trained on both people, but when you're decoding it, you can give it out as the decoding for the decoder B, which is trained to decode a representation of John Oliver. Now the reason that it works is, for the decoder, there is no difference, right? It looks at the encoding and it just thinks, okay, this is another encoding that I need to decode into a photo of John Oliver, because it's just been trained on John Oliver photos. For the encoder, it's no different, because the encoder is trained to encode both faces. So this one clever trick kind of gives you, if you look at the way that it works, it's going to give you an exact image, because it's going to capture the expression, it's going to capture the lighting, it's going to capture a bunch of these things that you need to capture for the encoding, for the decoding as well. So in this way, like, you have like a very simple way to have like a face swap performed of just one frame, right? One face and one frame. So now obviously when you can do it for one frame, extending it is fairly straightforward. To train, we have a bunch of these sources. You have Google Images, always a friend, especially if you're doing something with, if you're trying to use celebrities especially. If you have video sources, again, great, you can use FFmpeg for it. FFmpeg allows you to this. The example shown above is simply taking taking 2 frames from every second of video and like creating an image out of it. Image augmentation, always your friend. I think enough people have spoken about it over the last few days. Image augmentation, you can have flips, zooms, crops, rotations, lightings, contrast, saturation, a bunch of these image augmentation to like allow your encoders to train better. And then once your auto encoder has been trained, we come back to processing the video. Now processing the video is fairly straightforward, right? If you think about it, it's simply take a frame. If you find a face in the frame, crop the face from the frame using MTCNN. Give that cropped image to the auto encoder. The auto encoder actually like it encodes, and then like give it to the decoder, but give it to the decoder the other the person whose face you want to swap it with. Now, if you remember, I told you that MTCNN very helpfully gives us coordinates as well for where the eyes start and where the mouth starts. So you actually have a nice little bounding box as well. So you can use that bounding box itself as the place that you want to swap with. Save the frame, right? So that way, basically what you've done is, for one frame you've done it. Just repeat it for every frame, rinse and repeat until the end of the video, and you more or less have an entire image that is created, right? An entire video with a face swapped. Now, obviously, if you put this all together, you get really cool results like this. Yeah, I'm going to stop this here. Now, if you think about it, right, a lot of the things that are happening in this process is just a loop, right? So like when you're training, you're like training it in loop. In the deep learning terms, what we call an epoch. So we train it in epochs. For processing the image, we're actually taking each frame, so we're doing it in loop. For almost anything that you're doing, right? In the entire process, if you look at it, we are just doing it in a loop. The training is a loop, the production is a loop, everything is a loop. And that is something that computers are really, really good at, right? Doing a process repeatedly a million times in a row, right? And that is something that has made like deepfakes technology, especially over the last couple of years, become like this hub of a lot of research, right? A standard way, like today we talk about, the example that I gave you was just an autoencoder. People have actually figured out, instead of having autoencoder generate an image from the encoding directly, how about we put a GAN in front of it? Maybe you generate a different image and then the decoder tries to decode using that. There's like a lot of research that's going on in this subject. We'll talk a little bit more about this. So what we've spoken about so far is like the most straightforward way that you can generate a deepfake in. But over the last couple of years, especially, there's been a lot of research going on these. So, for example, one of my favorite papers, and this is back from 2018, is a paper called Everybody Dance Now. I would strongly suggest everyone like look up this paper. They released their code about a month back, I think, and I've been playing around with this code a little bit. It's an amazing paper with some amazing results, and I'll just play this as well for you. So I'll mute this because basically what's happening here is you see the source video on the left, on the top left, and this is the actual person. Now this person is not dancing in any way, right? But what they have done is they have actually extended the model that we spoke about just 2 minutes back, except what they've done is they've added an additional layer in between that does pose detection. So you can actually see for the source video, for every frame, they basically do key point detection using a pose detector. They have a pose detection algorithm in place. Then they use this pose detection algorithm in a very similar manner to what we spoke to generate what the frame should be if this person was there, right? To do it's not a face swap, it's an entire body swap using pose rather than facial key points. And you can see that the core of the algorithm is still the same, right? The core is still looking at it in the same way. A lot of research has gone in since then. Like if you notice in this video, this was in 2018, if I remember right, or 2019, I think. A lot of research that went in, you can see, you can still make out the difference that it's not a smooth video because you're looking at every frame by itself, right? It's not a smooth transition between frames. So you'll see like the hands cutting out every once in a while, things cutting out, things like that. So in the last year, there's been a lot of research in like how to make deepfakes look more smooth, how to make them like, how to have information from the previous frame actually be passed forward to the next frame to like maybe generate an average of multiple frames as what the final frame is going to be and things like that. And it's results like this that have like kind of brought deepfakes again into the forefront, right? Because as this technology gets more and more mature, what you're going to see is more and more proliferation of these kind of images and these kind of videos, right? So now let's go to something even cooler, right? This is something that came up I think sometime in the last 6 to 8 months. Again, a paper that came along with code, and that's something really cool, especially in deepfakes world, is that a lot of the papers that have been being published actually have a GitHub repository right there for you. For this paper specifically, and this I'm fairly certain is somewhere where the inspiration for the talk, the videos that are shown at the start of the talks come from, right? So if you think about it, so far what you've spoken about is you need to be training on two sources, right? You need to be training on the person who you are swapping with, and you need to train it on the person whose face you are swapping. But what if you're talking about someone like, let's to take a wild example, like Picasso, and you don't really have photos of that. Or you're talking about, let's say, Mona Lisa, right? You don't really have photos of them in different poses or different actions or different angles and different lighting and different this, right? So you can't really augment that much. And then this paper came out, which more or less, it's called first order motion. And the way that it does it is it's basically taking an image with a single image and it's trying to create a deepfake out of it. And their results are fairly amazing. So as you can see, right, there is no way for us to know what the inside of the mouth of Mona Lisa looks like, right? And you can see that you can obviously see how this method will have some glitches compared to the methods that we are trained on a bunch of data sets. But the fact that you can take one image, a single image, or like a very small sample set of images and create convincing looking deepfakes, especially for a lot of context, right, is purely amazing. The nice thing about this specific technique that we're seeing here is that for some reason this kind of became a meme, right? And there's an entire thing called the Bake no Motai meme, I think, if I'm not confusing with the terms. It's a Japanese term, and which is basically a Japanese song. And you can actually make your memes for this by literally running a Jupyter notebook. I've provided the link here. You can actually run this. You can upload an image and generate a deepfake out of it in less than 30 minutes, in 30 minutes flat, right? Which is a crazy amount of learning for a system to do. So this is kind of like where we are right now in terms of when you're talking about deepfakes technologies, right? You can literally, where we're saying that you can literally look at one image and generate convincing looking videos and convincing looking audio and convincing looking, and audio is a different subject, but like convincing looking videos for this. So then comes the next topic, right? So I've been talking about deepfakes for a little over 3 years, I think. And this slide actually was not part of my initial set of talks, right? But I think every time we say deepfakes, this topic has started coming more and more often. So we keep talking about, so it makes sense for us to like talk a little bit more about the ethics as well of methods like deepfakes, right? So first and foremost, right, I think a lot of people, like I mentioned at the start, were introduced to deepfakes in a very different manner than what we are seeing right now, right? These are very harmless examples. But the original, the moniker deepfakes itself comes from this user on Reddit who generated a bunch of pornographic videos using this method, right? And the fun bit is like he other than giving his name to this technique, the common name that is used for this technique, he's not a published researcher, he's not a published this. The guys at NVIDIA were in fact the people who ended up publishing this method quite and got all the credit for it. But deepfakes kind of became the user who like created a bunch of these, right? So the obvious question comes up like, was what he did ethical, right? And I think like as we spoke about a little bit during my sneak peek as well, it's really wrong for us to talk a little bit about ethics specifically in this use case, simply because of course there is a point to be made that technology cannot be like moved away from ethics, but at the same time when you have technology out there, it's really important for us to have visibility, right? The fact that the Wall Street Journal, the Washington Post, Wired, Guardian are speaking about it has led to this new genre of technology where they're talking about how do we identify deepfakes, right? How do we save ourselves from this, right? For a longest amount of time, we have said that sound has not been, like you'll see lots of times when like sound recordings are there, people would say that, okay, this is like an altered audio. But like video was usually considered to be proof, right, so to speak. But now even video is something you cannot really believe. So there's a lot of research that's going on now into identifying what a deepfake is and how we can identify it. And at the same time, there's obviously on the other side a lot of research going on how we can circumvent these identification methods, right? There's an Among Us game being played between researchers there as well. The second part of it is like it's kind of like a Pandora's box, right? And I think generally, like we spoke about it at the start, AI is usually as jerks, right? So if you think about it, till about 10 years ago, a lot of things that we take for granted today were not possible. Forget like takes a lot of time, were simply not possible. But in 10 years, the kind of leaps that we have made, and now we are kind of at a state of maturity where we're like trying to like come back to terms with what is possible, what cannot be done, what are the contexts that we're talking about, and so on, right? And just to give you an example of that, right, just in 2012, which is not even that long ago, it took Google a network of 16,000 computers and trained for 4 days on 6 million images, if I remember right, to identify what a cat is. Okay. Right now, you can train ResNet on a decent GPU at your home or 2 GPUs at your home in a couple of days. Okay. That's kind of the leap that we have made in the last 8 years alone. And leave aside that, right, with things like transfer learning and things, you don't really need to even do that training. You can have pre-trained models and like train on a few epochs and get like state-of-the-art results as well. The final thing that I want to talk about is applications, right? So when we say deepfakes, the autoencoder usage or the GAN usage, right, is something that has gotten to popularity with like specific use cases, and especially autoencoders I think are primarily shown because of deepfakes. But there are so many other use cases where like autoencoders are useful, right? And primarily any application where dimensionality reduction can give us gains is useful. And just to end up, I'd like to end up on like this one specific example that came to that I think the paper was published very recently. It's just about a week back that the news release came out as well. So and this is something that's really great, which is The guys at NVIDIA Research are using a very, very similar model to what we've spoken about in terms of deepfakes. But instead of using an autoencoder there to like do a facial swap, what they actually do is they have like a photo of the person itself transmitted over, and then they just do key point recognition of the stream. So instead of transmitting every pixel of the stream of my video, right, I can actually just do the key point recognition of my face and send those over. And the bandwidth gains that they have, you can see here, are ridiculous, right? There are 3 orders of bandwidth less. Now, it goes without saying that technologies like this go a long way to like make like video conferencing more accessible, to make remote work more useful, to make so many other things, right? Having like accessibility in places where there's little to no internet. And like I come from Goa, where like 2 Mbps is still considered the fastest internet there is, and lots of people still consider 512 kbps as a good way to like browse the internet, so to speak, right? But with most modern technology, it's next to unusable with those things. But like having things like this, where you're saying that we can make modern tech work with modern tech, but at lower bandwidths, right, is clearly a use case for a lot of research that's going on. And like I'll end up on this because like this is something that we are currently talking about like state of the art as of 1 week back. There's a lot of research going on, so I'll be open for questions either way, with like anything that you guys have on your mind. And like with that, I just end my talk. My slides are available at this place on GitHub. You can go and look at them. All the links that are there are all usable, and you can go ahead and use those. So thank you very much.